All right, so old business. Jared, I think, asked about what this means, this notation here. It means you take two derivatives, and this is what I should have written down yesterday. Okay, and I wrote I didn't write it. But this is what it means. You take the one derivative, then you differentiate it again, right? So that's the meaning of this. People just a long time ago, got tired of writing this out. The second thing, and I should have realized this too, I told you yesterday that the position as a function of time has to be smooth. You can't have a kink in it like this. Okay? This is actually a discontinuity in the first derivative. Just on this side, the first derivative, which is the velocity, is here, and it's different here. You can't have that, and the reason is this. Remember the acceleration, this is our definition of the acceleration. It's the limit of the average acceleration, the change in velocity with a change in time, as you shrink the time interval down, right? So as we shrink it down right around here, delta t goes to 0, right? But from just on one side to the other side, what's delta v? Well, it's the difference in these two velocities, these two slopes right here, which doesn't go to 0. So this would require, and this has infinite acceleration at this point, and it would require an infinite force, as we will eventually see. And you can't have an infinite force. So it's got to be smooth. Incidentally, in the elevator sketches there that we did, you know, I fit parabolas, right, between the two accelerating regions when the acceleration was not 0. Remember those parabolas? You have to impose that condition of smoothness. When you do that, this parabola, now this is, when I say I fit, this is just a sketch, okay? But the same thing would happen if you actually did it on a computer quantitatively. But see how it's smooth here? That, one reason that's, I don't know how to say this, you know, it has to be smooth, right? But it has this kind of other nice advantage. That nails down the parabola uniquely. There's one and only one parabola that will smoothly connect these two lines here. It's unique, which is what we demand in physics, right? Okay. Any questions about those two things? Okay, so we've set the stage now for constant acceleration in one dimension or rectilinearly. We've got these equations. They only apply for constant acceleration. They kind of tell you that because this a here is the, I guess they don't. This a has to be a constant. It can't change in time. These equations only hold for constant acceleration. So there are three equations we'll be working with. Here they are. We derived these graphically yesterday. There's an you can look for an analytical proof in the textbook. So we're just going to explore these today, and we're going to do it in two different ways. We're going to do demonstrations and problems. So let's begin with a demonstration. Okay, and it involves this. This is an old device. It's called an air track. Has anyone seen this before? Yeah, they tend not to use air tracks, but I like them, and I think they work well. This is a hollow aluminum rail with little tiny holes. I don't know if you can see the holes. And then pressurized air comes in. There's an air pump down there. So the air comes out of these holes, right, at a pretty good rate. And this glider, right, resting on here, will float on a cushion of air. So the friction will be very small. So let me show you this. So you can see here, that should look strange to you. That should look strange to you, right? Because normally there's going to be some kind of friction, slope. In fact, you know, here, right, a lot of friction. So there's very little friction here. So what's going to be the motion? I give it some initial kick. What do you think? Just what we will derive this, or we will explain this. But what do you think the velocity is going to be? This is a level track. How do I know it's level? Do I have to go get a bubble level and put it on top of here?
Velocity should be constant.
I can't hear.
Velocity should be constant.
Well, yeah, you're answering my previous question. Forget that right now. I moved on. We moved on. We will get back to that. Sorry. Sorry. How do I know that this is, how do I know that what you saw there looked like constant velocity, but maybe it was just, the track was tilted or, I don't know.
It's not moving unless you put some force behind it.
Yeah, okay, look, how do I know? I want to make sure this track is level. So do I have to get a bubble level? Yeah.
I don't see the moves.
Exactly. This has a built-in level. Here it is, right? Okay, so the first thing we should do maybe is just this. I'm going to carefully release it from rest here. See it? It drifted a little bit, right? Yeah, very little friction. Okay, and it's approximately level. Now, so you would expect with essentially no friction here that it would move with constant velocity, and we will we'll explain that later on in the course, okay? But I want to point out that we can actually measure it here, and that's what these things, these detectors here, are for, okay? So there's a light source, infrared light source, on one side. On the other side, there's the detector, which has a photocell. When the infrared light hits this photocell, a voltage is generated. Okay, so you can pick up on that voltage, and that's what these boxes do here. So when the glider goes through, it stops the beam. That's going to start a timer here, and then when it goes through again, it'll stop it, and we'll get the elapsed time. Right. So let me turn them on and reset them. Hopefully this will work. Did it work? Do you have the readings there? Okay, so what's the average velocity for the first gate, for the first photo gate here? So the average velocity is delta x over delta t. Delta x I measured to be 13.8 centimeters. And you tell me what's delta t? That's in seconds.
0.4387.
4387 seconds. Calculator? Can somebody calculate this? And we need confirmation too. Oh, somebody's got a calculator, right? Or a computer or something? Yeah, thank you.
31.46.
31.46. You didn't give me units.
Centimeters.
Right. Okay, this is wrong, isn't it?
It is one extra significant.
That's right.
My apologies.
No, don't apologize. And I was hoping to get that. I was hoping this would happen.
31.5.
There we go. Okay. What about, this is the first one. What about the second photo gate? So now, again, it's going to be the 13.8 centimeters. And now what is it?
0.4421. 31.2 centimeters per second.
Thank you. Okay, they're close. Now, you always have fluctuations, and I think we actually talked about this a little bit. Did we? Can't remember. There's always fluctuations here, but it is curious, isn't it? Which one's less? The one farther down. So we're probably to take more experimentation to confirm this. But what I suspect is this is the effect. The fact that this is less is due to drag. But we don't really know. It just could, Sometimes you do this. This one could be greater. That can happen. But we don't know. It's conceivable that it could happen just because of fluctuations. But it's probably, this is 1%. It's 3 parts out of 300 roughly. So this is a 1% drop or decrease in velocity. And it's probably due to the friction. Okay, any questions about,
So I might be trying to argue pennies right now, but Wouldn't it be impossible for the second time to be greater than the first time? Because you have to, with all other things constant.
No, that's the whole point of it. There's always fluctuations. You know? And you know, this track is not perfectly straight. It has, in fact, some of these the manufacturers will actually sometimes build in a slight curvature here so that you can do collisions. You can put a glider there and it won't drift like we saw, right? And the other thing is that it's not perfectly level. I got carried away there. And it's from the simplest thing. What if it has a slight slope here? This could be greater, right? Because it's going to accelerate. Right. Welcome to this is a real world here, right? This is an experiment. It can be greater. That's why we have a lab in this course, so you'll get used to this kind of thing. Other questions? Okay, so let's take these off. And what I'm going to do now is tilt the track. Here's a 1/2 inch aluminum block. Okay, so now what's going to happen? Suppose I release it from rest here. What's going to happen? Now, it has to accelerate, because initially it has no velocity, it has some velocity later. There has to be some acceleration. But it's not clear how what that acceleration is in time. In fact, if you look towards the end here, it looked like maybe it was moving at constant velocity, which is zero acceleration. So, we're going to go over this thoroughly, derive this when we do dynamics. The answer is this: for a straight incline track like this, called an inclined plane, usually is what people call it, the acceleration is constant. It doesn't change as you go along here. All right, let me see what else. Oh, right. So, if we release it from rest, look at this equation right here. For constant acceleration, we release it from rest, this is 0. We'll call our origin where we release it from rest, so we get x is equal to 1/2 at squared. In other words, there's a parabolic relationship. The position as a function of time is going to be a parabola that looks like this. And it comes in with no slope because we're releasing it from rest. So that's what our theory tells us. And you'll notice here that if you look at this at equal time intervals here, because of the acceleration, the displacement is getting bigger and bigger here. After some time interval, this tau can be anything. After some time interval, it's gone some distance d, right? If I double the time interval, what do I do for the position? It quadruples because of that squared. Again, here's a time interval. It goes 4d. When I double the time interval, I quadruple that, and I'm up here at 16. So we have this parabola. So how can we test this? Well, here's a simple way. And let's turn these off so I'm not distracting. Here's a simple way to do it. Remember the cheap metronome here? Okay, it's ticking off seconds. Well, that's not really important. The important thing is these are equal time intervals. So we're going to take that to be this tau here. So the glider should cover more and more distance as it goes down. If the acceleration is constant, it should have this feature here of doubling the time interval, quadruples that. So here's what I've done. You see these black pieces of tape here? Can you guys see those? Okay. We're going to look at, our reference here is the right edge of the glider. It starts here, okay? This is D. That's this right here. That I measured, okay? We will be able to predict it, calculate it, but that we don't know how, once we know what the acceleration is, but we're not there yet, okay? So I measured this distance D, just experimentally. I released it from rest, and after 1 second it goes there. Then what I did was, taking this, I established all these other distances by factors of 4. Or, well, by the square of the time. So it would go 2 squared, 3 squared, 4 squared. So if the acceleration is constant here, the glide, every time you hear, I'm going to release it, the glider on a click here, a beat. Okay, I'll release it. It should go here, there. Okay, that we're testing whether the acceleration is constant or not. So let's see if it works. 1, 2, 3. It was close. It wasn't right on, right? This is very sensitive. You can play around with this after class. It's sensitive, you know, of the release here. You're a little bit off in the release, and it just gets magnified as it moves faster and faster. The air gets magnified. So that's what happens there. But it's pretty close. I'm happy, because I know it can be a lot worse than what you just saw, okay? Okay, let's see what's next. Okay, so now, we're not going to do this. Now we're going to do a couple problems. As I told you, we now have, armed with these equations right here, there's just a whole ton of problems that can be solved. So we're going to do some simple ones, and then we'll do some more tomorrow, right? Tomorrow we'll have problems from chapter 1 and chapter 2, the problem set tomorrow. So here's the first one. Here's an intersection, streets with lights, okay? And the light's red. This car is stopped, okay? And this car, the person in this car has timed the light so that right when this person's car gets to the intersection, is lined up with this car, the light turns green. Okay, has anyone ever done this? I have. I used to do it all the time. It's really not a good thing to do. Why is it not a good thing to do?
Because of other traffic?
Yeah, because there are people out there who run red lights, okay? So, yeah, you just don't want to do this. So I stopped decades ago, all right? But that's the situation here. So this is like time t is equal to 0 here. They're both at the same location. Our motion is along this direction. This car is at rest at that moment. This one's moving at a constant speed of 20 meters per second. And right at this moment, this person accelerates with a constant acceleration of 8 meters per second. So, what do you think the question is? What's interesting here? This person has a constant acceleration. This person's going to be, A is going to be ahead of B. But what eventually has to happen? B will overtake A. So that's the problem. Find out where does that happen, what the velocity of B is at that point. So it helps, to appreciate this, it helps to sketch a graph. So here's a graph of position versus time. Here's the moment here is the origin of time. Car A moves with constant velocity, straight line. We know that, right? B has constant acceleration and is starting from rest, so it's a parabola that comes in with 0 slope here. We know that too, right? And we quantitatively know that. So you can see here, it's clear, no matter how low the acceleration is here, because it's a parabola, it's going to eventually, and its steepness, its slope increases, it's eventually going to intersect this line. And that's what we're after, the intersection here. This is, at this moment, B is overtaking A. And we're going to solve for the time it takes. We'll call that capital T, not to confuse it with the variable time here. And it's going to occur at some distance. We'll call that capital X. Okay, so that's the idea. Analytically, how we proceed like this. How do we describe this relationship here? Well, it's constant velocity. So the distance is the velocity times the time. And this is pretty obvious, and you'll get very used to this. But I just want to point out, even though it's trivial, but let me point it out. Look at this equation. Car B has no acceleration, right? This is 0. If V0 is constant, X0 is 0, so we just get that equation I told you. It comes from here. But after a while, for constant velocity, you're just going to be writing down, velocity is distance divided by time. It's very simple. So the distance is therefore the velocity times the time. because velocity is distance over time. What do we know about this? Well, we just talked about that. This is going to be this upright parabola of zero slope. From that equation that I just showed you, we specialize it to the case of zero initial velocity, and it's at the origin at zero, and we get just that one term there. And now we set them equal, right? We set them equal. This is the equation that we get. And now, everyone, almost everyone, what's the next step you're going to do here? Oh, let me say something in case I forget. VA is 20 meters per second, right? Why don't I just substitute that in here? Well, you can do it if you want to, but it's cleaner if you just stick with the algebraic terms until the end and then plug the numbers in. It's just a lot cleaner. It's more transparent. But you can do whatever you want. Okay? Now, getting back to this. What's the next step here? It's very tempting to do something here. We want to simplify this.
Get rid of the t.
Cancel the t. Yeah, but you can only do that if t does not equal to 0. This has actually two solutions. The math is telling us that, but sometimes we don't listen to it. One of the solutions is t is equal to 0. Is that correct? Yeah, there it is. Yeah, there's actually two solutions. So the math is doing we're asking the math, to give us all the solutions where xa is equal to xb. There are two solutions. We're not interested in that solution, so we can cancel. In that case, we can cancel the t's from each side of the equation. When something's 0, you can't cancel it from each side of the equation, right? Right? Okay, you can't cancel it. But discarding that solution, we cancel it, and then we find this, and I already, I cancel this t, one of these, and now the unknown here, I know VA, that's the 20 meters per second, I know the acceleration, that's the 8 meters per second squared, I solve for t, and I get this expression. It's also advantageous to do this algebraically because this is a general formula. VA and AB can be anything here. So that's another reason why I like to do it this way. But again, it's up to you. At this point, I substitute the numbers and I get 5 seconds. Okay, well now that we have the time, it's going to be easy to find the distance. How do we find the distance? You can plug it back into either of these. It's simpler to deal with the straight line. They coincide here, so you can use either expression here. But we'll use the simpler one. We just plug it right in. We don't even have to change this now that we know the time. And we get 100 meters, which, I don't know, I think that's kind of surprising here for this acceleration, This is, free fall acceleration, we'll talk about this in a few minutes, is 9.8 meters per second squared. This is comparable to that. But I'm sure this is right. It's 100 meters. The important thing for you to recognize is it exists, okay? Quantitatively, what it is, well, we just crank it through, and that's what we got, 100 meters. What about the velocity of B at that point? How do we get that? Well, now that we know the time, we go back. This equation tells us B starts off at rest. This is 0. We now know the time. We just multiply by the acceleration. So those three equations are under. We haven't used the third one yet, but we will. Don't worry. They're underlying everything, all of our quantitative stuff here. So we get 40 meters per second. So that's kind of interesting. At this point, car A is moving at 20 meters per second. Car B is moving at twice. Is that a coincidence? If we change the numbers here, would this still be twice that? You would guess that it wouldn't be, but it turns out to be a property of a parabola, that this slope is twice that slope. And hardly anybody knows that anymore. I'm sure, it was a big deal a couple hundred years ago, but nobody knows or cares. But I just think it's kind of interesting. And it is actually a check on our solution. You can see from our graph here that the velocity of B has to be greater than the velocity of A. It's also physically obvious because it starts off very slow, and the only way it's going to overtake it is it's got to be going faster. It's got to be going faster than B. It's obvious at this point that B has to be going faster than A. And our solution shows that. So that's actually a consistency check. It's 40. Okay, there's one more thing I got to tell you here. Okay? Now, you'll notice how we very carefully solved. We have this algebraic expression for the overtaking time. We plugged the numbers in with their units. We canceled the meters, canceled one of the seconds, and we get that, right? And that's fine, and it's sometimes good to do that. But it does get tedious after a while. So from now on, almost completely, you'll see what I'm going to do in the notes here is, and in the problem sets too, is I'll drop the units. Now, how can I do that? Well, if everything is in SI units here, I know that the answer has to be in SI units. So if I'm sure that I've got everything in SI units here, everything's correct, there's no need for me to write down the units. This has to be in the units of seconds if everything is in SI units. Now, that includes, you know, if you've got something in centimeters and something in meters, you've got to take care of that, of course, right? So SI means meters, kilograms, and seconds. So if everything is in meters, kilograms, and seconds, and not centimeters or microseconds or whatever, the answer has to be whatever this variable has to be. In this case, it has to be time. So we'll do that procedure, okay? And it's up to you if you feel, once you feel comfortable, you can drop these units too. But if you're ever worried about it, I would put them in there. Make sure that it's right. And it's a dimensional check too. You know, you see we cancel the meters here, we cancel the seconds, we get seconds. What if we didn't get seconds? What would have to be true? We made a mistake. Okay, so it's a check. All right, question?
I'm going through the algebra in my head, and maybe I'm the only one. But how are you getting t equals 0 for the first solution of that?
If I set the t equals 0 here, the left side is 0. If I set t is equal to 0 there, the right hand is 0. So it's a solution to the equation. It's that simple. Yeah. Any other questions? Okay. So typically what we do is in lecture we do a few examples and we just beat them to death, right? The problem sessions will move more quickly, but it's just good in the beginning, I think, to talk. There's a lot to talk about here. You know? There's a lot going on. Okay, here's a classic problem. I remember this from high school, believe it or not, and it's a class. There's a reason why it's a classic, and I'll explain to you. So here's a train, and it's always a train. Nobody knows what not. It's a train moving has constant acceleration, and it's actually decelerating because it has initially, over some intervals of motion, it initially has a 50 meter per second velocity, and then it goes down to 30. So here's a sketch, right, of velocity versus time. It starts off with 50, it goes down to 30, and I draw a straight line because we're told that the acceleration is constant. And then we're given that the 30 meters per second occurs 160 meters down the track from here. We're not told the acceleration, and we're not given any information about the time. So this, when you first confront this, this looks confusing. Okay, this takes a little bit of thought. Now I've represented the information here on this on the sketch here. Here's the initial velocity. Here's the final velocity. The distance is the area under the curve. The displacement is the area under the curve. So that's why I've written the 160 and put shading in it. Sometimes that helps to do that. So you could actually graphically solve this problem from here, but that's. So I just want to mention, I wasn't planning on mentioning, I wasn't even thinking about it, but you can take a graphical approach, okay? You know, we took a graphical approach to come up with the equations that we're going to use, right? So that means for any specific problem, you can use that graphical approach, but it's just easier to use these equations. And here they are. Let me remind you, here are the three boxed equations. Okay, so maybe some of you are starting to see where this is leading to. We have no information about the time, and we don't know the acceleration. This has two unknowns in it, right? This, we don't, again, we're led to the no time equation. We don't know the time, we're led to this equation. Is that equation going to be useful for us? Can you look at that and see? See, we know the initial velocity, we know the final velocity, we don't know the acceleration, but we know the displacement. This is one equation and one unknown. So that's why I think this problem is a classic. It's first confusing when you look at it, because we tend to think in terms of these equations. But there is the no time equation here. Now you could get this information out of these two equations, but you'd have to eliminate t between equations. But here we do it once and for all. This is so that's why it's good just to use this equation. It saves yourself a lot of trouble. You really don't have to have this equation, but it makes life much easier. So let's see what we get with the no time equation. Here it is. I'm doing this algebraically, all right? You can see that I've brought the v0 squared over on the left side of the equation, and then I've divided by 2. I'm isolating a. So I've and you don't have to do it this way, this is the way I like to do it. I've algebraically isolated the a, our unknown here, a, and I get this formula. Now I plug the numbers in, everything's going to be in SI units, right? And so the answer will have to be in SI units. So I'm not going to put the dimensions, the units down here. I get 30 squared minus 50 squared. I get 2, and the displacement here is 160 meters. And I get an acceleration of minus 5, and it's got to be meters per second squared. If we had not gotten a minus sign here, we would have made a mistake. So you always want to do these simple checks. And the reason is, we know this thing's slowing up. This is negative slope. Well, we're done. Once we know the acceleration, we can get, what are we after here? Oh, the time. The total time, the time going from here to here, we can get it from the simple first of the 3 equations. We can solve this for the time. And I've skipped a step here. I'm going to put that back in when I edit it. I can, similar to here, we solve for the time and then plug the numbers in. We now know the acceleration. And this is nice. You'll notice that it's negative in the numerator and negative in the denominator, so we get a positive time. If we'd gotten a negative time, there's nothing wrong with negative time. But in this case, it's got to be positive. So sure enough, it is. It's 4 seconds. Okay, so we're going to do a lot of problems like this tomorrow. And this one I intentionally put in here because it's a classic problem, and it really, you need to realize this equation can be very useful when you don't know the time. So that's why I call it the no time equation, right? Okay, any questions about that one? Okay, so the next thing that's natural to talk about here is free fall, because it's constant acceleration. So what does free fall mean? It's not real clear what free fall means, okay? So I'll be careful, I'm trying to be careful here. But free fall is vertical motion in a constant gravitational field where there's constant gravity, like near the surface of the Earth. Now the reason I have to say constant gravity is because if you start to go up higher and higher in elevation, what happens? If I release an object near the surface of the Earth, it's going to have a certain acceleration, because initially it has no velocity, later it has some velocity, so there's been an acceleration, right? If I do the same thing higher up, what happens? It's less. The acceleration's less. You all know this, right? But near the surface of the Earth, and in the absence of air resistance, okay? In the absence of air resistance, the acceleration is constant. In other words, as this thing accelerates down here, just like the inclined plane over there, it just has it keeps its acceleration. The acceleration is constant. The velocity gets greater and greater at a uniform rate. So that's what we mean by the acceleration is constant. It is also independent of the body. So it doesn't depend upon the mass of the body. And of course, this is the famous Galileo thing with the wooden ball and the lead ball, right, that released from the conveniently leaning Tower of Pisa. So that was very convenient. Incidentally, it's not clear if he actually did that or not, I think. Anybody know anything about this? I think it's not clear that he ever did it. But it's a good story, right? So, near the surface of the Earth, the universal acceleration here doesn't depend upon the mass of the body. Okay, and in the absence, when air resistance is negligible, this is the value of the acceleration, 9.8 meters per second squared. Later in the course, we will talk about how you can, well, this can be measured in the laboratory, and we'll do it in one of the labs, I think. You can also calculate it. If you have knowledge of the Earth, how big the radius and mass of the Earth, you can also calculate it. We'll do that later on in the course. Okay, so let's do a demonstration. Let's start off with some demonstrations, and then we'll do some problems. So here's a baseball, piece of paper. If I release them from rest, if they have the same acceleration and I release them from rest at the same height and at the same time, they both should strike the floor first. Do you think they're going to strike the floor first? Does anybody, what's going to happen?
Baseball.
The baseball. Are you sure?
Yes.
Okay. I learned this one at a community college. I'm not kidding you. Okay, you guys see? 1, 2, 3. Pretty much the same, right? So what's happening here? You know, air resistance depends very much on geometry. By scrunching this down, I've strongly reduced the air resistance. It's approximately in a vacuum, right? Now the next one is kind of similar. Oh, sorry. So what you were thinking is this, right? But what about this? What do you think is going to happen? You all know the answer, right? This is unstable. And if you take fluid mechanics, you'll understand why. By unstable, I mean it's just not going to go straight down. This is the stable look, and even this is not that stable, but this is very unstable, and you can see it here. Oh, it happened, did everyone see that? It happened a little later than I thought it would. Let's try it again. Yeah, okay. So again, the ball beats it, but when you compress it like that. Okay, here's another paper. We're going to get some use out of the physics book here. That's what it looks like in case you... Okay. So, I'm not going to compress the paper, okay? And I'm going to release these two objects, the same distance here, at the same time. What's going to happen? Everyone's not saying anything right now. Okay.
Well, I mean, are you going to crumple the paper up again?
No, I'm not going to crumple the paper. That's the word I'm working. I was looking for a word there. It's crumple. Thank you. Early. No. I'm not going to crumple the paper. I promise you I'm not going to crumple it.
First, yes.
Okay. But let's not stop there. What about this? Oh. You see that? There's no sleight of hand here. Okay, we occasionally do that in physics. I don't know if I'll do it in this class, but we don't do it much. So, I don't know the full explanation for this, but part of this is, any bicyclists here? Drafting? Right. In fact, I heard last year when I taught this course that if you're behind some like big truck, you actually hardly have to pedal at all.
You know nothing hardly pedal?
What?
You have an electric assist on that bike. 30%, just saying.
So, you know, the air is being diverted by the book, and I think two things are going on here. You know, so it's cutting down on the drag because it's diverting the air, but it stays so close. There could be some kind of suction effect here because this is very, you know, close. Also, when the flow gets diverted, vortices get created that go like this, and they actually push it that way. That may be what happens when you're right behind a truck.
Since you're talking, I'm just curious because I've seen it now. Is that why they put on the wings of the planes now? Is that why they put, you see the tips of the like the end of it are angled up? Is that
Yeah, that's because of, you got to take PC1121, fluid mechanics. I don't know if you guys are going to take that. I'll bet not. But come by my office and we'll talk about that. That's to cut down wingtip vortices, which can cause trouble.
They lowered gas consumption by some astronomical amount, like typical things like that.
But you also
Right.
see on the trucks nowadays too, they have those things that come out and kind of angle it.
Yeah.
It's all wind resistance.
Yeah. So they're cutting, in that case, they're cutting down on drag. Yeah, in all of these cases. But the question is, sometimes it's not too obvious. These things on airplane wings, that's actually to cut down on these things called wingtip vortices, which again, ultimately it's going to cut down on the drag. But the effect that it has can be different from one case to the next. Yeah, it's an interesting story. Oh, here's a classic demonstration. It's not working too well, and it's called the penny and the feather demonstration. So there's a penny that just hit there, and can you guys see the feather? It's moving very slowly. Okay. Sometimes it gets stuck. So this, there's air in there. So now what I'm going to do is pump out the air. That is. Okay, so I'm going to close the valve, switch off the pump, disconnect this, and now do the experiment again. Now I think you can see the feather is not quite moving the velocity of the penny, but it was moving very slowly before, right? And it is moving close to, it does have close to the acceleration, but it's getting hung up right in the beginning. I think that's what's happening here. Well, I don't know. And just to show you that, we can go back to the beginning. Where's the, oh, there it is. Back to the beginning again, okay? So, there's dramatic evidence that the acceleration is, in vacuum, is constant. Okay, so now what we're going to do is two problems. This is a classic problem. This is one way of finding the height of a building. You take a heavy object, a stone or something like that, and make sure nobody's down here, and you drop it and you measure the time it takes. You release it from rest at the height of the building and find the time it takes before it hits the bottom. And you can determine the height of the building from that. So let's see how this works. Let's suppose that the time is 3.5 seconds that we measure here. It's released from rest. How tall is the building? We'll calculate that, and we'll also find the velocity of the rock just before it strikes the ground. We'll call this our origin. This is y is equal to 0. And here I've actually written out the general equation that we're going to use. I've written out this is absolutely general, and we're going to apply it to this situation. Okay? What's our final y? 0. In the beginning, you want to do it the way I'm telling you. After a while, you won't think about it anymore. But you want to carefully go through here. What's y naught? Well, that's what we're calling h here. That's y naught. That's the initial y value. So we're going to replace y naught with h. What's v0? 0. And 1/2 gt squared. And this t then, we've applied this equation over the full motion here. This is going to be, we'll call that capital T like we have in the past. That's the total time, the time of flight. Right? We have one equation and one unknown. Because we know t, that's been measured. We know g, we don't know h. So we can find h. And here this occurs over 1/2 at or gt squared occurs a lot. We just plug in the numbers, 9.8 meters per second squared. This is all SI units, so the answer has to be in SI units, and it's 60 meters. It's a pretty high building. All right. What is the velocity just before the rock strikes the ground? Well, we know the acceleration. We know the time. We use this simple equation. We're releasing it from rest, so that's going to be 0. So now that we know the time, we just plug it in, and we get that the velocity is minus 34 meters per second. I don't know if I mentioned this yesterday, I might have missed it in the notes. The speed is the magnitude of the velocity. Although a lot of times people don't respect, when they say velocity, they're meaning speed. It's usually clear. But technically, the velocity is a signed quantity. Speed is the magnitude of the velocity. Okay, now here's an interesting question. This is not going to be the height of the building because of air resistance. So is the actual height of the building greater than, or less than, or perhaps equal to 60 meters? Okay, I hear a lot of different, what?
Less than us.
Yeah, that's, I think most people would say that. Most people probably think it's less. But let's go back and look at this. In fact, maybe I can stick with this slide. Air resistance, what is air resistance going to do to the time of fall?
Increase.
It's going to increase it. So the actual height of the building, this is an upper bound. It's actually less than 60 meters. What did you guys, I've already forgotten.
Say less.
Oh, you did say less? Okay. So I made a mistake. I think for some people the reaction is, oh, it should be greater. Air resistance causes something to be small. But you're right. I'm sorry. It's going to be the actual height of the building will be less. Let's see here. Yeah. Okay.
In the labs, are we going to calculate the coefficient of friction then?
Okay. Now, coefficient of friction, which we will study in here, relates to sliding friction.
Oh, just sliding.
Okay. This is air drag, which is sliding friction has approximately no velocity dependence. There's an impeding force. We'll go over this. That doesn't depend upon the speed. But air resistance, that's not true for air resistance. When something's moving slowly, there's very little air resistance. It increases with velocity. So those are two different cases.
Okay.
And we will not take it. So what was your original question?
So the original question is, are we going to be calculating the friction that is acting on
The air drag.
air drag on objects that are
No.
dropped, or coefficient of friction is
There is, we will be doing problems with the coefficient of friction. In the laboratory, to shorten that experiment, I can't remember. I think we may or may not in the laboratory do coefficients of friction, but we'll definitely do problems on it. As far as doing calculations with drag, that's a little tough. We can do terminal velocity calculations. In fact, that brings up the next and final example here that we're going to do, terminal velocity. Well, you all have heard of terminal velocity. We're not going to get into it. We're going to get into it in depth later on in the course. But for right now, we will just naturally it'll naturally happen here. So here's the final problem here. We've got a baseball, again, that's been hit, and it goes straight up. Oh, this is, it's tempting to think this is the trajectory. This is not x, it's t, okay? So this is what's happening in time. What's happening in space is it's going straight up and straight down. And we know that it reaches a height of 40 meters, okay? And that's all we know. That's all we're given. Okay, all right. And here's a series of questions. What's the acceleration? So it goes up and it comes down. What's the acceleration here compared to the acceleration there? It's a trick question. I think somebody said it. Yeah, it's the same acceleration. The tendency of some students to think, well, I don't know what they think, but what you think, but it's the same everywhere here. There's nothing interrupting that acceleration. No forces, as we will eventually see, are coming into play. There's just the force of gravity, and that gives rise in a vacuum to constant acceleration. What's the velocity at the top? We talked about this. It's turning around at the top. Okay. Actually, the technical name is it's a turning point. It's a nice phrase, right? So at that moment, the velocity has to be 0. What are the initial and final velocities, and how we have to calculate this, and what's the time of flight? So we're not given any information on the time here. So you tell me. You go to you look at the no time equation to see if that's going to help. So here's the no time equation. Got no time in it. We don't know v0. We know h. We know, we can find the initial velocity. And if you solve for it here, you see it's the square root of 2gh, a common expression that we will see many times in this course. We plug in the numbers and we get 28 meters per second. What's the final velocity just before it strikes the ground? No, assuming negligible drag. Well, you know, it's going up, it's slowing up, it's speeding up. Each of these is just a time reverse situation of the other one, right? What it's doing here is just going backwards in time. So what's the, for a vacuum. So what's the final velocity? It's going to be the same. The speed's going to be 28 meters per second. It's going to have, we ought to put a minus sign there. Did I do that? There's a minus sign because it's going in the opposite direction. Now, what I just told you, that's a legitimate argument, but it's in the equations. If you look at this equation, all right, we can solve this for the final velocity. What is, we just set, what's the displacement over the whole path here? What's the displacement? Zero. So I just zero this out. So, and oh, here we go again. Maybe this look familiar. So here's what I get. So what can I do next here? Can I take the square root? So does this imply v equals v0?
V equals plus or minus.
Right, we're missing. It's possible to have, we need to put a plus or minus in here. Because v here, you know, this can be positive or negative, and when it's minus, when you square it, it's also a solution. And that's the solution here. Clearly it's going in the other direction. So the fact that the final speed is is equal to the initial speed, or that the final velocity is just the opposite, it's negative, it comes out of the equations too. So here I need to add something here. So you fire a bullet straight up in the air, comes back down, hits your head. Are you going to die? I'm trying to phrase this in a dramatic way. What?
Probably not.
That I don't know the answer to the question. You guys probably have better feel for this than I do. But I think you could be right. You're not going to necessarily die. Maybe we should put it that way. And what's the reason? Well, yeah, air drag, right. So especially it'll be even worse with the tumbling, I think. So this final speed, being the initial speed, is for no air drag. The effective air drag, which is always against the motion, is going to slow this thing up when it comes back down. And so it may not kill you. Does anybody know the answer? Is it what?
Mythbusters did it.
Yeah, it'll probably hurt. I agree with that. What?
Mythbusters did it a few years ago. They did different angles where they fired straight up, because the spin of the bullet straight up would hit the very top where it stopped. When it fell back down, it doesn't have that same spin, so it loses its velocity. And they tested it at certain angles. There was some angle of like 60 degrees of where it kept its same spin trajectory, where it did come back down and maintain that same velocity. But I forget
approximately the same. There's going to be a loss of energy, as we will describe. It's a big deal. Probably the most important thing in the course is the whole what energy is. We'll get to that. But it's got to be less. Otherwise, you'd be violating, you'd be ending with more energy than you started with. But, okay, interesting. Oh, there's one more thing here. Thank you. There's one more thing, the time of flight. Here's our simple, for constant acceleration, the velocity changes uniformly. It's a straight line. We can just use that and apply it over the whole motion. We can apply it over the whole motion here and get the time of flight. Students, when you ask students to calculate the time of flight, almost always they'll calculate the time it takes to go up and then double the answer. But you don't have to do that. The equation works. It's constant acceleration. You can apply the equation from the initial point here to the final point here, and it's actually simpler. Okay, so we'll do problems tomorrow. We're over. Okay, thanks.